In this work, we first introduce the ObjectFolder real dataset that includes the multisensory measurements for 100 real-world household objects, building upon a newly designed pipeline for collecting the 3D meshes, videos, impact sound, and tactile readings of real-world objects. Based on these 100 real objects and the 1,000 multisensory neural objects from our earlier work, we introduce a benchmark suite of 10 tasks for multisensory object-centric learning, centered around object recognition, reconstruction, and manipulation with sight, sound, and touch. Our results demonstrate the importance of multisensory perception and reveal the respective roles of vision, audio, and touch for different object-centric learning tasks. By publicly releasing our dataset and benchmark suite, we hope to catalyze and enable new research in multisensory object-centric learning in computer vision, robotics, and beyond. Next, I will introduce our work in more details. When we see an object like this, we want to model multiple aspects of it. Maybe how it looks from a different viewpoint under different lighting condition, how it sounds at a different impact location with different force, and how it feels, maybe at different surface locations from different contact orientations, and maybe how it behaves under different interactions in different tasks. It's clearly important to completely model an object in a multisensory way. In our earlier work, ObjectFolder, we propose to virtualize the real object, their intrinsic properties, into some neural-in-place representation we call object file, and query the object file with extrinsic parameters external to the object. We can render the corresponding multisensory readings of the object. And we build a dataset of 1,000 multisensory neural objects called ObjectFolder. In the dataset, each object is a uniform object-centric and implicit representation, and the dataset is easily accessible to the community as a standard benchmark for multisensory learning with vision, audio, and touch. And all objects are platform agnostic and compatible to different virtual environments. Okay, these multisensory neural objects are great, but all multisensory data are obtained through simulation. For some objects like this one, it will listen to the simulated audio and the real impact sound recording. You can see that there's still a large gap between sim and the real, especially for the high-frequency components. We need the real dataset to potentially calibrate the gap between simulation and the real. So here we introduce a dataset called ObjectFolder Real that contains multisensory data collected from 100 real-world household objects. We design a tailored data collection pipeline for each modality. For vision, we scan the 3D meshes of objects in a dark room and record high-definition videos of each object rotating in a light box. For audio, we build a professional anechoic chamber with a self-designed object platform, and then collect impact sounds by striking the objects at 30 to 50 surface locations with an impact hammer. For touch, we equip a Franca Amiga Panda robot arm with a dual-side robotic finger and collect tactile readings at the exact surface locations where impact sounds are collected. Next, I will give a quick overview of all benchmark tasks in our benchmark suite, starting from object recognition. Our first benchmark task is cross-sensory retrieval, where the model is tasked to take one sensory modality as input and retrieve the corresponding data of another modality, for example audio, from a pool of sensory observations from different objects. It can also retrieve from the pool of tactile images, all within the same modality. The second task is contact localization. Given an object and the local multisensory observations of the contact position, it can be a visual image, impact sounds, or tactile readings. This task aims to predict the surface location where the contact happens. The next task is material classification. Given an RGB image, an impact sound, a tactile image, or their combination, the goal of this task is to predict the correct material labels for the target object, ceramic in this case, from 7 material categories. Next, I will talk about the object reconstruction task in our benchmark suite. The first task is 3D shape reconstruction. Given an RGB image of an object, a sequence of tactile readings from the object's surface, or a sequence of impact sounds of striking different surface locations of the object, the task is to reconstruct the shape of the object from these multisensory observations. The next benchmark task is sound generation of dynamic objects. Given a video clip of a falling object like this, the goal of this task is to generate the corresponding sound based on the visual appearance and motion of the object. Here's an example of the sound generated from a baseline method. The next task is visual-tactile cross-generation, which can be divided into two sub-tasks: touch to vision. Given a tactile reading on the object's surface, predict the corresponding local image patch where the contact happens. And vision to touch. Given an image of the local region on the object's surface, predict the corresponding tactile RGB image that aligns with a visual image patch in both position and orientation. Finally, I'll talk about the object manipulation tasks in our benchmark suite. The first manipulation task is grasp stability prediction. The goal of this task is to predict whether a robotic finger can successfully grasp and stably hold an object based on either an image of the grasping moment, a tactile RGB image, or their combination. In this case, it's a successful grasp. Here's another example of a failed grasp and the corresponding sensory observations, from which the model makes correct prediction. The next manipulation task is contact refinement. Given an initial pose of the robotic finger and observations from the target finger orientation in the form of either a third view camera image, a tactile RGB image, or both, the goal of this task is to plan a sequence of actions to change the finger's orientation to contact the point with a different target orientation, as shown in this trajectory execution example. The next manipulation task is surface traversal. Similar to contact refinement, the goal of this task is to plan a sequence of actions to move the robotic finger horizontally or vertically in the contact plane to reach another target location on the object's surface. Here is an example of trajectory executions with an iron plane object. The last task in our benchmark suite is dynamic pushing. Given example trajectories of pushing different objects together with their corresponding visual and tactile observations. The goal of this task is to learn a forward dynamics model that can quickly adapt to new objects with a few contextual examples as shown on the left. With the learned dynamics model, the robot is then tasked to push the object to a new goal location as shown on the right. Thanks for your attention.